All right. So it's another day and another stream. But yes, I think I've been out for a while. That's because I've taken on a new job. It's a new role. It's interesting and stuff. So I've sort of been caught up with all of that. Now I finally found some time to like get back to uh, streaming as such. And without spending too much time into what I've been doing, we will come to that if and when time permits. Today, I want to talk about Rust GPU, right? And this is sort of a continuation of the compiler stuff that we've been doing so far, the Rust compiler series. Um, and this happens to be something that I'm working on, um, not directly on Rust GPU, but something to do with Rust and compilers and the intersection between both of them. So I thought I'd pretty much, you know, take a look at Rust GPU and see how it's, uh, you know, how it works. Um, so to quickly get started, let's actually look at a couple of notes that I've made. All right. So the other thing is you might be seeing uh, a bigger screen of some sort. That's because I basically got a new home setup. So just let me know if things are okay and you're not there's there aren't any you know issues as such. All right, so to quickly just talk about what Rust GPU is. So if you remember, I did a stream that talked about Pleuron, which is an excellent project. It's a very good project where basically said that's the replacement or the equivalent to what MLIR is, except that it's entirely written in Rust. Um, so that's one side of the compiler stuff that I've been looking at. The other one is directly looking at backends. I've already talked about the Cranelift backend in quite some detail when I was learning, how things work over there. Uh, Today, Rust GPU that we're going to be looking at is just another Rust backend. In other words, what do I mean by backends? Just to sort of recap that, in compilers, you've got the front end, the mid end, and the back end. The front end is pretty much what we call the Rust compiler. The back end is, technically not Rust. Uh, the de facto standard that Rust uses is LLVM. It's effectively a project that lets you take Rust code in a certain format and compile it down to various target machine code. It means if you're trying to compile code for, let's say, x86, you'll get that through LLVM, ARM, and a whole bunch of other targets as well. I've talked about this multiple times. Rust GPU is another one of those backends. The idea of Rust GPU is, as the name says, you will take Rust code and directly compile it down to code that will effectively run on your GPU. In this case, it's not directly run on the GPU because every GPU vendor has their own particular instruction sets and uh, their own instruction sets, and they're running that instruction set on their GPU. What Rust GPU will do is it will compile Rust code into a format called SPIR-V. SPIR-V stands for Standard Portable Intermediate Representation. Um, the V, I guess, stands for, let's actually check that. I haven't checked that. So, SPIR-V full form? Yeah, Standard Portable Intermediate Representation V. Um, I don't think V stands for anything. I guess it stands for a number or something like that. Anyway, so it's another IR, another intermediate representation. But this intermediate representation is designed for things like GPUs. the reason I say things like GPUs and not just GPUs is because this instruction set prioritizes, things like parallelism and the constructs that you use to write parallel workloads. Um, and pretty much it can target other things as well. For example, SPIR-V is also a target for things like encoding and decoding video and digital signals, etc. So there's a whole bunch of other applications as well. But this is something that is maintained by the Chronos group. They came out with the IR. And as they say, it's the standard IR for parallel compute and graphics. So it's not just graphics workloads, which are technically inherently parallel, but you can also use it for compute. And that's exactly my area of interest, the parallel compute part. So SPIR-V is not that big in the parallel compute part as something like, let's say, CUDA or ROCm or whatever that vendor specific compute uh, ecosystem that we currently have. So each vendor has their own. NVIDIA has CUDA, AMD has things like ROCm and a whole bunch of other things, and there's OpenCL and a lot of different stuff. We've already been through that. SPIR-V isn't just another format, it's another IR that you can target. And if you do target that IR, you will be able to pretty much, there's a way to take SPIR-V and turn it and have it run what you called NVIDIA PTX, which is the instructions that will be running on the NVIDIA graphics card, or AMD's own instruction set, or Qualcomm, or anybody else who has built a GPU, pretty much supports SPIR-V at this point. There's a path to move from SPIR-V into those native instruction sets. That's what SPIR-V is good for. And I believe the folks at, sorry, these good folks over here, this started out as a project by a company called Embark Studios. They sort of built this, the initial one, but I believe now that's sort of moved into somebody else is taking custody of that project and to truly sort of give it some attention because it's been stagnant for a little. Embark Studios is an actual for-profit company. They have other things to do. So the open source ecosystem in Rust decided to sort of take it up and sort of push this forward. That's a very good thing. And currently, here's what here's what it looks like. So if you want to sort of present this on your screen, here's the equivalent, what you'd say, SCADA code or GPU code that will run on your GPU. So you can see there's this tiny little sun over here. There's a nice little blurry effect. It looks cool and stuff. I don't know anything about graphics, but that's fine. But our goal, or rather today, what I want to actually explore is how do you take this, which is Rust. It's pure Rust. You can see that. Of course, it's got some proc macros, etc., which are always a headache. But it's pure Rust. You've got your let mute. You've got you got functions. It's just Rust. It's pure Rust. It's not like a version of Rust that is a variant of Rust or something like that. No, it's just actual Rust. So that's the interesting part. How do you take Rust code and convert that to this thing called SPIR-V, which is the intermediate IR? And then from there on, you can just take that and like this one is apparently using WGPU as the backend for SPIR-V. That means you take SPIR-V code and then you push it through what's called a framework. A WGPU is it's WebGPU, right? It's an implementation of WebGPU in Rust called WGPU. You can basically target any GPU using that. Just that. I think we've talked about that as well. So effectively, you take this and you want to convert that to SPIR. That's ideally what you want to do over here. So how do we do that? So what Rust actually does is it you don't actually take Rust code and convert that to SPIR-V directly, obviously, because Rust has its own intermediate representation. And I spoke about this quite a bit, but here's again a recap. So when you have Rust code, what actually happens? What does rustc, the compiler, actually do? There's like 4 stages so far. There's a bunch of different things in between as well. But you take your Rust code, you create an abstract syntax tree, and you do a bunch of things like macro expansion, name resolution, etc. And then you move from that state to what is called a high-level intermediate representation, which is HIR. Here's where you do your type checking and type inference and all of that stuff. And then you come to the typed version of it. So HIR doesn't really have a lot of types. In typed HIR, you'll pretty much everything has to have a type. So here's where you do things like pattern matching and exhaustiveness checking, etc. And then finally you come down to MIR, the mid-level intermediate representation. Here's where a lot of the interesting stuff in Rust actually takes place. So your Rust source code will end up in mid-level intermediate representation form. And you see that MIR is typed, basically it has types. It is what is called SSA. It's an SSAIR. I've talked about this in the past, not important, but just know that every value that is assigned to a variable is only assigned once. So that's called single static assignment. But anyway, here's where you do your things like borrow checking and a bunch of optimizations before we pass off this MIR to LLVM. We sort of do the borrow checking over here and the optimizations. And then the other important form is we do monomorphization. And then monomorphization is got a nice little, yeah. So here's what happens. You can write generic code in Rust. You can say something like foo-t. I hope this is visible enough. Hopefully, yeah. So anyway, this should be visible enough. So there's a foo-t over here and a bar and a baz-t. You could pretty much instantiate different instances of that, like a foo-u32, a foo-f32, a baz-bool, and something else. All of these are concrete instances of your generic, definition. What Rust actually does is, because it believes in zero cost abstractions quite a bit, it's going to go ahead and at compile time create an instance of every single item, every single definition that you have. If you've invoked it with whatever T that is, it's going to fill in all of that. So you're going to have an instance of a foo-u32, a foo-f32, all of that. That's basically monomorphization. You move from polymorphism to monomorphic code, right? So that's pretty much that's pretty much what's happening at the MIR level. And once you do that, you then hand it off to the backend. Backends over here can be the standard one, which is LLVM. It can be Cranelift, which is an up and coming one. It can be GCC. I don't know when that's going to be built. There is actually a backend called rustc codegen GCC, but I'm not too sure where it is, what it is doing at this point. And then there are custom backends, like what we're seeing over here, which is called rustc codegen _ SPIR-V. So this backend will basically take code that you write in Rust and produce SPIR-V. So to sort of give you some sort of feeling for what does SPIR-V look like, let's actually take a look at that first. So I've got 2 ways to show you that. The first one is, let me just pull this up. When you compile, there's a lot of stuff over here, so just have to bear with me a bit. Yeah, so this should be in dependencies, maybe. Yeah. Right. So this is what SPIR-V looks like. All right. It's an intermediate format. It's extremely simple. You'll start with things like, okay, a capability. What are the capabilities of this particular module that you're writing? It's a shader. It is based on the Vulkan memory model. It uses the Vulkan memory model. So SPIR-V pretty much is tied to Vulkan quite closely because the same guys that are building Vulkan are the same guys that are building SPIR-V. And it's going to expand in its scope. But for now, you'll see a lot of Vulkan stuff here. And then you'll have things like entry points. Okay. So there's 2 different shaders over here. One is a mean. The other one is, fragment shader. The other one's a vertex shader. And then you have things like op execution mode, etc. We'll come to all of that. And then you've got decorators. You've probably already seen them. Just let me show them to you. So this stuff that you're seeing, SPIR-V fragment, this frag coordinate and push constant, all of this, they're marked as core decorators. And then everything is typed in SPIR-V. It is again SSA. Like you, for example, you'll be able to see this. I'd say that I want a float with 32-bit precision, and I'm going to call that person float. The moment you say this, you're never going to go ahead and reassign this variable. You can use it elsewhere on the right-hand side, but you're not going to reassign that anywhere else. That's basically single static assignment. And you will see all of this. This is pretty much what SPIR-V looks like. So you take this stuff, basically this stuff, and you want to convert that to this stuff. Yeah, that's the goal. And you might wonder, oh, big deal, we can do that. Well, that's the whole point of compilers. So type information, the layout of things, the ordering of things, the sequence of things, whether or not this is the best way to construct these sequences of instructions. This is the most optimized, space efficient manner to do this. A whole bunch of things will pop in. So you're just doing mapping from this representation to this. Actually, not this, but the MIR representation to this. Okay. So that's kind of what the Rust GPU backend does. And the moment you're in SPIR-V, you can go from, I think there's a nice little somebody put out, I don't remember who put this out, but I remember, yeah. Oh yeah, the same guys. So if you were to look at SPIR-V, is this good enough? Yeah. Yeah, that's right here. So everybody's targeting SPIR-V, all right? So the moment you have your code in this IR, in this representation, you can now move into, you can target Apple, the metal stuff. You can target CUDA, I believe this is CUDA, right? Let me just make that bigger. Yeah. No, this is DirectX. Yeah, this is DirectX. So whatever DirectX is, you can target that. You can target OpenCL, and then a whole bunch of other things. Like, it's up to you. What do you want to do? You can also go backwards. Uh, it's an IR. You can go back, forward, whatever. You can do a lot of stuff. Yeah, and then you can target Vulkan. Yeah, this is the path to the other GPUs like NVIDIA and all of that stuff. And if you just want to target DirectX, you sort of go through DirectX own intermediate language called DXIL. So that's the reason why SPIR-V makes so much sense. It's like it's not there yet, but it's potentially going to take the position of this universal IR for parallel compute workloads, right? So anybody just write stuff, target SPIR-V, push out your, have a compiler to push out your code, to take your code and turn it into SPIR-V, and then you can target all these other platforms that you have, right? So that's a bit of a history of what this particular CodeGen does and where Rust fits in. So Rust MIR is what's going to get converted into SPIR-V, as I mentioned. Now, with that context, I think I'd want to keep this short because I'm going to go through a bunch of these videos. It's going to be a little more of a deep dive. I'll just get through the pieces where, I've been exploring the Rust GPU crate and trying to understand what it's doing. Like the basics, how do you do this mapping? How are you actually going to map it? But even before I do that, I want to show you how. So I've already run this command, so I already have the MIR dump here. And I also have this directory. I'll just show this to you. I'll show you the commands as to how you can go ahead and create them. So what happens when you actually write your Rust code? The Rust C part is going to take over when you ask the compiler to compile it, and it's going to produce MIR. What does MIR actually look like? Here's what MIR looks like, right? And I'm only showing you the shader fragment stuff. There's also other stuff, like you will see that there's all this other stuff over here. Not important, but what's important is this. Let me just minimize that. you will see that where's our fragment shader? So yeah, so the main vertex shader is over here, and then you've got the main fragment shader over here. So the main fragment shader and the main vertex shader are the two shaders that I'll be talking about throughout this video. And the implementation for that is over here in shaders. Just pick the simplest shader, go look at them. This is the implementation, right? So if this is the implementation, the corresponding MIR, that is mid-level intermediate representation, sort of looks like this. All right. So you'll have some temporaries first that say, okay, I at least need two variables. Then I'm going to have two basic blocks, and variable temporary number two is going to be alive right now because I have to explicitly say that when something is um, accessible and when something's not accessible, when something is live and when something's dead. That's what it means. The storage is dead, the storage is alive. So you take that and then you call glam vec4, which is sort of here. That is going to run the whole thing, and then whatever value you get, you assign that to 2. And then pretty much whatever you see here is like for like. You'll be able to see that over here. But except that this is in a different representation. The reason you use representations is because for things like reasoning, optimizations, understanding, clearly, right? That's sort of uh, what's happening over here. So you will take something like this and you will convert that to the previous form that I was showing you, which is, where did I put that? That was here, here, release. Yeah, by now you should sort of realize that it's not very straightforward when you're working with something like this, like IRs. It should be, but yeah, it'll take some time. So all of that, whatever you saw over here, this stuff is effectively going to be mapped over here. Okay. And I'm using the word mapped because it's actually a mapping. You're taking one representation and then you're creating the other representation, or you're building the other representation. So it's the same information, actually. You don't want loss of information as well. That's being mapped over here. The reason you want that to happen is because you can just pass it off to, that pipeline. All right, so that's the context. A couple of things that you'll probably need to keep in mind is the way the SPIR-V backend is being built is obviously we're going to be dealing with MIR, so we need to know how the Rust front end, which is rustc, constructs MIR, right? So we're going to need to touch the rustc front end. We're going to need to look at things like basically plug into the Rust compiler, like how, and there's some things that you need to know, not a lot. If you know these pieces, I think you can just start reading the code and start making it sense. If you dump right into a Rust compiler, you're going to obviously the Rust compiler is a massive project. I don't know, maybe a million lines of code. I don't know, probably, but it's a pretty big project. And the things that you need to keep in mind are the most important thing is it has something called a type context. This is basically a global context. All right. And this is what holds all your, what are called arenas. So whatever you see over here, saying, okay, this is a basic block. These are the instructions in there. These are the temporaries, all of that stuff. What are the types? What is the layout? You want all that information to basically do the mapping. So that stuff is pretty much stored in what's called arenas. Arenas are, you don't want to keep allocating memory and managing all of that stuff. Arenas are a concept that's used. It's used everywhere, especially in game development as well. Over here, at least with rustc, what's happening is it enables fast allocation, and there's simplified lifetime management. Simplified because once you allocate that stuff, you don't deallocate it. You either drop the entire arena or you just let it be there. So, and partly I think that's why Rust Analyzer takes so much memory when it's, for example, just looking at this, and if you look at this, Rust Analyzer is taking about 4 gigs of memory. That's, I am assuming that's because of all this stuff going on. I'm not too sure, but there's something. So this global context is what's going to keep these arenas. Interning is where whenever you come across some item in your compilation, you know, phase, in your compilation process, you would see that, okay, these things, like for example, there's a name. You might see that name appear 100 times in different places. You don't want to like keep reallocating or doing all of that stuff, or even recomputing whatever you need to do with that name. So you just compute it once and then you push it off into a table, right? So that's sort of interning. And then there's this query system. This is what Rust sees. Yeah, this is a new thing about Rust C, where compilers usually do this. You take one input and then there's like there's many phases. So at each phase, you take one input, push out one output, take in one input, push out one output. The query system is a little different, apparently. Um, so only when you need something, you can query for it, and then it could lazily do the compute if it needs to, and then give you the answer back, and also cache whatever results of that compute is. So that stuff is also part of the compiler. So you just need to know that part. So with this little bit of information, you can start reading at least this backend. That's how I would put it. There's also some more context for Rust GPU. The first thing is uh, this GPU, this backend is pretty old in the sense that um, it needed to be. Um, uh, there's some hacks in there. Okay, I think these hacks are the first things that need to be fixed by the community. For example, um, I already told you this backend, the way it's built is it plugs into the Rust C infrastructure and then builds the backend. So one of the things that they plug into is called this rustc codegen SSA. So previously, the Rust compiler had only one backend, that is LLVM, and it was called rustc codegen LLVM. Now, but that was very tightly tied to LLVM. So what they did is they sort of went about saying, okay, we can refactor this in such a way that we can accommodate an easy way to add more backends. So the basic thing that they did was all of the code involved in that, all the types and the functions and the implementations that were LLVM specific, they made them generic and sort of pushed them into one crate that they called rustc codegen SSA. So any backend that uses the SSA, IR kind of forms, they can simply just use that crate and plug into that and start working with it. And that's what I mentioned over here. So rustc codegen SSA is the backend crate that we will use as part of the SPIR-V backend. And it's also used by pretty much LLVM, Cranelift, GCC, and all of them apparently will be implementing the same thing. All right. Yeah. So that's, and rustc Codegen SPIR-V is also going to be implementing primarily when I say it plugs into the rustc front end, I mean that in this crate, there are a bunch of traits. You want to implement those traits, and then you become automatically a backend, like with anything in Rust. You implement some trait, and you become that thing, right? That's what rustc Codegen SPIR-V is over here. Great. So there's some traits. We'll come to this part, hopefully in this stream itself. CodegenBackend, extra CodegenBackend, a bunch of different methods. Not important. But yeah, the first thing I did was I started looking at examples, right? Because if you want to understand some code base that is alien to like this, let's see what sort of examples they have, etc. And if you can see over here, I didn't make this bigger, so let me make this bigger. If you see over here, there's this folder has like the crates. Here's where you have the main crate, which is this is the backend. Everything that is to do with building the actual backend is based in here. Some types to support this backend, and this SPIR-V builder I'll talk about this. This is what's going to actually construct the SPIR-V. So it's a SPIR-V builder. It'll take the information that you're providing it through MIR, and then you say, okay, construct this particular pattern, construct this thing, construct that. So let's say there's a type in MIR. You want to map that type into SPIR-V. This thing is the one that's going to be doing it for you. All right. And then there's SPIR-V standard. This is the standard library, where obviously you can do the mapping great, but you also want to provide some, like the Rust standard library, you want to provide something for SPIR-V as well. To say, okay, here's how you can work with SPIR-V. That's all that stuff over here. All right. And as you are actually reading this, you might, as you can already tell by now, you really need to know how to get your MIR whenever you're working with this. So there's a bunch of different ways to do that. There's some environment variables you can set that will dump out a whole bunch of MIR. Okay, and this is interesting because as I said, MIR has all these, there's all these optimizations like constant propagation, copy propagation, all that stuff. After each of those, before and after, is going to give you what happened to the MIR. So if you see the MIR at the beginning, let's just say somewhere here, just say here, it looks quite different. But let's say we go to the end, like there's about 22 passes or whatever. This is pre-CodeGen, right? So this is what it looks like. And then post-CodeGen, this is what it looked like. Sorry, this is before and after that particular pre-CodeGen phase. And after this, there's also another phase, I guess, because it'll look a little more different than this. But anyway, so that's MIR, like debugging MIR when working with SPIR-V. That's a good thing. And then there's this other thing that I also wanted to show you. So I've already run this, so I'm not going to like run it. So if you go into, let's say, one of these simplest shader crates, where's that? Here. You go into one of these crates over here, and then you run, and let me just run this. So if I say, not dump, but I just want to run, yeah, I want to run this. So actually, no, I want to go into the crate. So builder, I believe this is the one, right? Yeah. Okay, so if I go in here and I simply run, I keep forgetting these names, you will get this. This is the actual MIR that, it's in the control flow graph. So if you want to look at this visually, you can just take this and you can go to something like any graph online editor and paste that. And then you'll actually get the complete visual flow of things, all right? Even better is, this is like, it's also got some CPU code in there. You don't want to see all that. That's why you see this stuff. I can simply go out of this and into, yep, Zeta, and now run that same command. And I get a much smaller one, which is easier for me to sort of make sense of. So yeah, here's what happens when I do that, right? So basically, this is the fragment shader. This is the vertex shader. And then you see your 4 basic blocks. So you can pretty much do a little bit of inspection, look at the control flow graph, how things are working, etc. So that's good. And yeah, finally, well, at least let me just cover this example part, and then I'll show you what, at least the first element where we end up doing the mapping for at least a single type. Let me see if I can get to that part. The examples over here were not really helpful. The reason is because what I want to do is understand how this backend works. That means how are we taking SPIR-V? Sorry, how are we taking MIR and how are we producing SPIR-V? The examples over here, what they actually do in a nutshell is they go ahead and already compile this particular crate. That means they compile the backend. And then every example that you write, it's going to be supplied to that backend and it's going to do the job and then spit it out. So you can't really do things like debug step through, breakpoint step through, and all of that stuff, at least not with the example. Okay. So you need to figure out a different way to do things. And that's kind of what I noticed. The example over here, it'll instantiate what's called a SPIR-V builder type. That's generally how you interact with the backend. So this is the single type that lets you interact, but that's not going to give you a lot because the implicit notion over here is that you'll be working with a pre-built, backend. Of course, you can do all those code gen argument things and dump stuff and learn about stuff, but I'd actually like to walk through a flow at least to understand what's going on. So that's what the examples are for. You can try them, you can test them out, etc. The best example that I've seen so far is, okay. The best example that I've seen so far is you go into runners, you go into WebGPU, and you take the builder one. This is the simplest one. And you will see that, there's a new SPIR-V builder that's created. And just this one method build does the whole thing, all right? It's going to invoke rustc with all the arguments. That's what I mentioned over here. Validates the target, the prerequisites, locates where this backend is compiled and present, any build flags that you've provided, runs a cargo nested build, all that stuff. It's sort of something that you see happening here. So it doesn't give you much, but at least you know some bits and pieces that, uh, what are the pre-processing steps that usually happen before you pass stuff off to rustc code. That's what you get here. Then, now with that said, the actual thing that you'd be interested in is the backend. So the first thing that you need to do is when you sort of get into the backend, when you're trying to learn about the backend, is when you go look at this crate, you'll be like, okay, uh, what is going on? All right. There's a whole bunch of stuff. And then you'll start seeing this particular crate for a long time till you realize that you didn't read the documentation properly. So what actually happened is the backend is a little bit of is a little hacky. The reason I say that is, you remember I talked about the rustc CodegenCx SSA crate that's present in the Rust compiler source code. That crate is we are actually using a patched version of that crate because the way SPIR-V is built is it uses this thing called alloca. Alloca is an LLVM instruction. So basically, typed allocas are what this SPIR-V backend uses, and that sort of changed in between. Right now, there's no typed information in the new implementations that are part of the Rust compiler. So we're no longer using that. So old Rust code expects typed allocas. We don't have that. So the new Rust LLVM uses what's called opaque pointers. This is not important. Just know that there's a reason why we're using a patched version of this crate, this particular crate, right? So because of that, we sort of need to patch it. So how do you do patching for something like this? Well, you write a build script. The job of this build script, among other things, the main thing is to create this. And that's going to be the interesting part because that is placed somewhere in your debug folder in build. You have to go hunting for it. Yeah, somewhere here. So yeah, here, this is the patch crate. So it's in the target folder somewhere, and you'll see that. So we're basically patching that and using the patched version of this. And this thing has to change. I guess that would make things a lot more simpler because opaque pointers, I presume, again, I'm not an expert, so I presume, I don't think it should be that difficult because all you're doing is this. There's usually this instruction in LLVM, which basically says, okay, there has to be type information associated with your pointer. Here, you don't have that. That's kind of what, you know, we need to avoid. So, yeah. the opaque pointer stuff is, plus we're not even depending on, this is not even an LLVM thing, right? So we need to figure out how we can do that. Yeah. So once you know that the backend does this patching stuff, then let's come to the next part. So there's like three very important data structures that I've identified so far. Minimize this a bit. Oh, sorry. Let me go back. So there's three different data structures that you should sort of pay attention to. Obviously, one's called SPIR-V CodegenBackend. This is the driver. This is the thing that's going to actually do your mapping from A, that is MIR, to SPIR-V. Okay, and then there's also two other things. Where are they? Just build them out. Yeah, there's CodegenCx, and then there's BuilderSpirv. Okay. Not so by the name, you can now, just looking at the names, you can say, okay, this is the backend. This is the context for that backend. And this backend is going to use this struct to actually construct the SPIR-V once it's done, saying, okay, I have this MIR type. I want you to produce this SPIR-V type, map it. And then you'll have to do all this, you know, whatever you've mapped, you need to put it in the right storage bucket and all of that stuff. So there's quite a few pieces involved, right? Uh, so that's kind of what uh, we need to be doing. And since I'm going to go overboard over here, I'll just leave you with these three things. And the other piece that I'm going to talk about is at least the first part. So when you look at the CodeGen crate, and you see that, this is the function that is used whenever you supply an environment variable saying dump mir, this thing gets called. Block listed is just for, you don't want to be mapping things that are not important, like debug info. Like you want to print some debug thing. You don't want to like map that. That's useless because that makes no sense on the GPU. Anyway, so you have the zero size struct over here called SPIR-V CodeGen. And the most important thing is you implement this particular trait. This makes it a rustc backend, right? And as you can see, this comes from, okay, this is renamed over here. This is actually rustc CodeGen SSA. And where is it renamed? Let me show you that. Yeah, you can see that over here. You'll see that we're calling it this specifically, but it's actually, this is renamed to this. Anyway, that's not important. So once you implement this, you get this method, the CodeGen crate. So perform the code generation for the entire crate. That's what it means. And then it internally is going to go ahead and call the rustc CodeGen SSA crate. And this is not going to do the actual code generation. This is actually going to do a lot of setup. All right, all this stuff, if you actually go read it, there's a whole bunch of things that this thing does. Among them, there is something called async code generic coordination. It's going to spin up a bunch of threads and then hand off, because when we do code generation, we can pick and choose code generation units and then pass them to each thread and compile them in parallel. So that's exactly one of the biggest gripes of Rust. You can do this thing. That's kind of what happens here as well. And a whole bunch of other things are set up. But somewhere in there, in the CodeGen crate, sorry, where am I right now? Yeah, somewhere in here, in this CodeGen crate, if you just go to the very end, you will see that it basically takes the B that it takes, which is the backend, and it calls that backend's compile CodeGen unit. This is the SPIR-V backend's actual code generation piece, and it's defined elsewhere. In other words, it's sort of defined here. So there's a extra trait that you implement, which is extra backend thing. In there, you will have compile code gen unit. And this is pretty much the first thing that's going to go ahead and perform the actual code generation. So It does a whole bunch of things. For example, we're going to go ahead and take the global context, pull out a single CodeGen unit, and then create a CodeGen context for it, and then you know arrange them in order or whatever it is that we were talking about. And then mono items are basically the monomorphized items that are part of the CodeGen unit. So CGU is basically CodeGen unit. Okay, all that stuff happens here. I will go through this in more detail as we go along these video series and as I learn them. But effectively, you have something called predefine, and then you've got define. The predefine is like your C header stuff. So even before you uh, start doing all the mapping and stuff, if you come across elements that you haven't seen yet, so what you want to do is you want to have this header file that says, okay, these are all the things that are in your uh, mappable thing, whatever you want to map it. So it's like a header file. And then you actually do the mapping of the implementation and the define. And this is pretty much the correlation over there. I'll go into that in more detail, but here's just to jump into predefine and show you what happens. So let's say you're looking at some static. So you've defined some static in Rust, and you want to map that to MIR. So when you say predefine, it's going to come here and say, okay, let me just do the predefined static map for that particular static from MIR to SPIR-V, right? Yeah, you'll see a bunch of types that sort of eat your head over here. But just note that this is kind of what's happening. You can't directly jump to this because you'll have to go ahead and look at where some of this is. So this stuff is in, where is that? Yeah, it's here. So you'll see that predefined static is actually part of this backend implementation, and you'll be able to see that up here. So quickly, let me just talk about at least this part so that you know at least the header portion. You will get a flavor for what's happening over here. So when we say go ahead and predefine the static, what we're trying to say is give me the for this particular instance, for this particular definition ID, whatever you're trying to actually map, it has an ID. From the global context, create the instance. So this instance can be a static, a function, a type, whatever it is. You got an instance of that. You get its type. You're basically saying it's fully monophized. You get the span as well. Span is not important. It's just the location in code, the line number, column number, etc. And then look at this. You are effectively going to go ahead and get the SPIR-V type for that particular instance. That's a map over there. That's exactly what you're doing. And then once you get that, you're going to use this declare global function to actually spit out, for example, let me show you in the SPIR-V itself, what happens. So if I ever encountered a static in Rust, I would probably declare it and show that in yeah. So that would probably be something like this. Okay. Sorry about the whole IntelliSense thing. It'll probably show up something like this. All right. It's a variable. We effectively spit out this particular state in here. All right. So if we went through this whole thing and we declared this global, declare global is going to be spitting out a SPIR-V instruction in some container somewhere, and it's telling you that okay, it's going to be storage classes private and all that. I'll come to the storage classes part. There's something called storage classes in SPIR-V which talk about where is this data going to be stored. Unlike the CPU, it's not just the RAM or the cache. There's different areas. So you've got the CPU's RAM, you've got the GPU's RAM, you've got caches, you've got within the GPU, you've got you've got partitions, so a bunch of things, right? So those things, and plus the way it's used. For example, if this is used for shader IO, then you also want to like specify that. So all that stuff is happening whenever you've done the mapping, and then you go ahead and construct the corresponding SPIR-V type. Yeah, I hope that's sort of, and you can do the same thing for, let's say, predefine a function, right? By the way, this thing does not do the implementation, it just does the, uh, you can say the header file definition kind of a thing, right? Okay, so that's where we are at this point. Let me just go back to where we started out. Yeah, we were here. So this is going to take a while. Don't sort of get worked up about that, because we're dealing with things like translations, and then there's a whole lot of context involved. So you might want to like, this might look a little daunting, but it is not. Let me put it that way. If I could get it, I think anybody should be able to pick it up. So yeah, that's pretty much what's happening over here. And then I'll talk about what a code generation unit is, and how the SPIR-V builder is actually doing the building. There's something called a local builder as well. At least this should give you some context of what's happening over here. So this is a graph, sorry, a flowchart that I put together where I said, you take each code generation unit, which is a collection of monomorphized items. You predefine the symbols for each of them. That means you basically do the header definition thing, and then you do the definition thing. Then you build an entry wrapper, finalize that, and then you return the compiled code gen unit in what is called a module code gen. All right, so that's pretty much what we're doing over here. What I'm yet to figure out is how would I not go to the example route and then do use SPIR-V builder, etc. I just want to like, I want to like construct some MIR and then walk through which portion of the backend is being triggered, like just flow through things, etc. That way I'd have a much better picture of understanding how this is being built and maybe even contribute, right? So yeah, and this is the block list part that I was talking about. Okay, so I hope that's that's gives. I mean, if somebody's just looking at this for the first time, I hope that's what do you say, clear enough. I'm pretty sure I didn't do a good job, but I hope at least it gives some starting point. Saying, okay, here's how I could probably understand this. Oh, and before I go, there's one more point that might prove very useful. There's this lovely person called Tim Jones, I believe. He's written, he's basically put together a playground for shaders where you don't have to go through all that. You just want to see, okay, if I give you this Rust code, what kind of SPIR-V is going to be pushed out, right? You can probably write, and it doesn't work for everything. It's quite simple. Okay, but it'll give you an idea. So you can write the same SPIR-V over here and see Rust code over here and see what SPIR-V's output. And it also works with other things like Metal, Slang, Wigzel, which is WebGPU's shading language, etc. All right. Okay, so that's kind of what I wanted to sort of cover, which is basically what is Rust GPU, right? Its current status, its inner workings in the sense, how would we go about understanding it? And if anybody's interested in, sort of providing a little more, feedback as to whether I got things right or wrong, because I just was working on this for like a couple of hours in a day, maybe. Got my Saturday, managed to put that. But I think it's a very nice way to first understand things like how you can write custom backends. A, B, the process, how the pipeline is being orchestrated. using rustc CodegenSSA SSA, and then building your own stuff, whatever your backend is. Right? Okay, that's it from me. Hope you find this useful. Please leave a comment if you have any thoughts or questions or feedback. Thank you. Bye-bye.